Remember, there are four variables that describe a gas: pressure, volume, temperature, and the amount. These four variables can be combined in a single equation called the ideal gas law. The ideal gas law is very useful when doing calculations involving gases. It can be used for pure gases as well as mixtures, and is often used in conjunction with other gas laws. So the ideal gas law is PV equals nRT. Comparing this to the other gas laws we've talked about, you'll notice there's a few differences. One that may stand out to you is the letter R. R is a universal gas constant. Since it's a constant, it always has the same value. This is the constant written with the units of liters times atmospheres divided by moles times Kelvin. We'll talk a little bit more about that in a minute. The other difference you may notice when comparing the ideal gas law to laws like Boyle's, Charles, and Gay-Lussac's is that the ideal gas law involves all four variables. So there's none that are held constant. The other thing that's a big difference between the ideal gas law and the others is that the ideal gas law is looking at a single set of conditions and is not looking at a change in conditions. This can be helpful when reading problems and trying to solve them, because oftentimes students confuse a problem involving the ideal gas law with the combined gas law. But remember, in the ideal gas law, there's not an initial and final set of conditions. Now back to these units of the gas constant R. It's important to remember that if you're using this constant in your equation, in order for the units to cancel out, the units of your variables must match them. So what I'm saying is that when you're using the ideal gas law, if you're using the R constant shown on this page, P is going to have to be in liters. Oh, I apologize. P is going to have to be in atmospheres. Right here. V is going to have to be in liters. Right here. The amount is in moles. Right here. And the temperature is in Kelvin. So just to say it again, when you're doing the ideal gas law, you'll need to make sure that the units that you're using to plug in for the pressure, volume, temperature, and amount match the units for the gas constant. So let's go ahead and try a few problems. So this question says, determine the pressure of nitrogen for 0.45 moles, that's N, the amount, at 25 degrees Celsius. Remember, no matter what the gas law, you have to be in Kelvin. So that's add to 73, and in 10 liters. That's our volume. So in this case, recalling that we have four units: pressure, volume, temperature, or amount, four conditions. When we look, they've asked us to find pressure, and they've given us the volume, the temperature, and the amount. So we can plug this into the ideal gas law. Pressure times volume equals the amount times the gas constant times T. PV equals nRT. So let's plug in our numbers. So pressure is what we're looking for, and we're going to multiply that by 10 liters. Then that's going to equal our amount, 0.45 moles, times R. Okay, I would like to move this over. I'm sorry. I'm going to move this so I have a little more room. So pressure times volume equals moles times R, which is 0.0821, liters times atmospheres, moles times Kelvin, times the temperature, 298 Kelvin. Now, before I solve this completely, I probably should have checked before I start, and I think I did it mentally and didn't talk to you about it. These are the units for your R. So really, before I started, I should have checked and made sure the units I am using also are the units in R. And you see that they do match, and so I just started. But you need to check that, because if they didn't, for example, if they gave you milliliters, you would need to convert it into liters before you plugged it in. So to solve this problem, down here, I see that I need to solve for P, so I'm going to divide 10 onto the other side. The top is a number, and you could have already solved for that. I'm just rewriting it. I'm going to include the units here, even though it looks like a lot, so we can see how they cancel. 298 Kelvin. That's the numerator, divided by 10. Now, just looking at the units before we plug in, liters cancel, moles cancel, Kelvin cancel, and you see right here what we have left is atmospheres, which are our units for pressure. So if I take 0.45 times 0.0821 times 298, that's on my numerator, and I divide that by 10, I get 1.1009. Two significant figures seems reasonable because they gave me 2 here. So I'd say 1.1 atmospheres. And that would answer my question. So rereading the question, determine the pressure of nitrogen at those conditions. And so this is the pressure of the nitrogen. Now notice I really didn't use the information that it was nitrogen. That's because any gas at these conditions would have the same pressure. Because remember, the ideal gas law works for any gas or mixture of gases. Well, let's try another one. And this example says, if a cylinder contains 10 grams, so they give me my mass. And they say it's carbon dioxide in 8 liters. That's my volume, because liters is a unit of volume, at 298 Kelvin. That's the temperature, because Kelvin is the unit for temperature. And this time they also want to solve for the pressure. So again, I have 4 units, and I've been given 3 things and asked to find a 4th. But wait, R has a units of liters times atmospheres over moles times Kelvin. Well, I have liters in my volume. I'm looking for pressure, so it will be atmospheres. And I have temperature. But look here. In order to solve the problem, I need the amount in moles. So I'm going to have to convert the 10 grams into moles. This requires me to remember that to go from grams to moles, I'm going to need the molar mass of the gas. And so I have carbon dioxide. And so looking on the periodic table, carbon is 12.01 grams per mole. Oxygen is 16, and I'm going to multiply it by 2. So that would be 32. So if I add those 2 together, the molar mass is 44.01 grams per mole. So I will divide by the molar mass. so that my grams cancel to convert the 10 grams into moles. And to 3 significant figures, I get 0.227 moles. So in this case, it was important that I knew the gas was carbon dioxide because I needed to find the molar mass in order to convert the grams that I was given into moles so that I could use the ideal gas law. So let's go ahead with the ideal gas law. So I know that it's PV equals nRT. I have all the information I need to solve for P. So P times the volume, which is 8 liters, equals the number of moles, which I had to calculate from the grams, times R, which is a constant. It always is going to equal the same thing with these units, times the temperature, which they gave me. To solve for pressure, I'm going to divide both sides by the 8 liters. And rewriting, so just so you can see what I'm doing, that this part would still be the same. That's the numerator, and I'm going to divide that whole thing by 8 liters. Again, just checking out the units to see why it's important. Moles cancel, the liters cancel, Kelvin cancel, and that leaves me with atmospheres, which makes sense because that's a unit for pressure. So 0.227 times 0.0821 times 298 Kelvin. Divide that by 8 liters, and I get 0.69421. It keeps going. Again, I think looking at the 8 liters, 2 significant figures is appropriate. So I have 0.69 atmospheres. And so rereading the question, it says, if a cylinder contains 10 grams of carbon dioxide in these specific conditions, what is the pressure? So I have calculated the pressure of the carbon dioxide to be 0.69 atmospheres. Now let's do one more problem, kind of along that same line, just so you can see. It says a cylinder of helium gas has a volume of 30 liters at 2.1 atmospheres and 303 Kelvin. Remember, a gas is described by 4 variables: pressure, volume, temperature, and the amount. In this problem, I've been given volume, pressure, and temperature. So I can find the amount, but this amount is in moles. The question says, what is the mass, which is in grams? So first what I'm going to do is find the number of moles. After I know the number of moles, I can use the molar mass of helium to figure out the number of grams. So let's plug in. So PV equals nRT. And this time I know pressure. Oh wait, before we start, let me check my units. So R is liters, atmospheres, moles, Kelvin. So I have liters, atmospheres, I'm finding moles, and Kelvin. So I'm okay. I don't have to convert any of my units. So pressure is 2.1 atmospheres times the volume times 30 liters. This is going to equal the number of moles, which I don't know, times the gas constant times the temperature, which is 303 Kelvin. So to solve for N, I'm going to divide R and T over to the other side. So I have 2.1 atmospheres times 30 liters on the top, and I'm going to divide that by 0.0821 liters atmospheres moles Kelvin times 303 Kelvin. Looking at the units, the atmospheres cancel, liters cancel, and the kelvins cancel, leaving me with moles. So plug this into your calculator. 2.1 times 30 divided by, and I put mine in parentheses, 0.0821 times 303. And I get 2.5325. I'm going to round it to two significant figures, so I get 2.5 moles. Now the question asked me for mass. So I'm going to have to convert moles to grams using the molar mass of helium. And so the molar mass of helium I can find on the periodic table. And the molar mass of helium is 4.003 grams per mole. In this case, I put the 1 mole on the bottom so that the units cancel. So if I take 2.5 times 4.003, I get 10.0075 grams, so I get 10 to two significant figures grams. So this, if I have a cylinder with helium at these conditions, inside of it would be 10 grams of helium.